So we're going to look at the graphs of radical functions, and I'm going to start off with the function f of x equals the square root of x. Just a real basic function. And if I take an xy table, or I'll call it an f of x table, and plug in some values, I'll start with 0 and 1, and I want some numbers that are easy to take the square root of. So we'll just use perfect squares just to make this simple. So 0, 1, 4, and 9. Okay, then you take the square root, right? So the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3, and we're dealing again with the principal square root because I don't have a negative in front, so it's always a principal square root here. If I were to try to plug in negative numbers, like if I put a negative 1 in, then the square root of negative 1, again, we can't do square roots of negatives yet. We're just going to say not a real number. And that's the case for all negative inputs. Okay, so there just aren't any points there. And so if I look at the graph of this thing, I don't need to look at the negative x values because negative x values give me no real number. There's nothing there. There's no point on the graph. And so we just need to look at 0 and then numbers on the positive side to the right. So 0, 0 is on the graph. And then if I were to take this out, 1, 2, 3, 4, 5, 6, 7, 8. Let's go out a little more. 9. That's good. That gets us all 9 values. And then I want to go up here. 1, 1. So I'm going to go up to 1, 1. And then 4, 2. So you go over 4 and up 2. And then we're going to go over 9 and up 3. It might be a little more over there. Okay, so somewhere in there. And what you'll find is that this graph does not go straight up like our linear graphs. Instead, it has a curve to it. It starts at 0, 0, increases a little more rapidly, and then kind of levels off a little bit. Now, I probably didn't graph that real well, but something like that. Okay, and this curve then is the graph of the square root function. And let's see. And it has some properties. One property is that it has an x and y intercept at the origin. Another property is that it just goes off to infinity. As you plug bigger and bigger numbers in, you're going to get bigger and bigger numbers out. And so the domain and range can be found. Remember, the domain and the range are the inputs and the outputs. So the domain gives you all the x values covered by the graph, in this case from 0 out to infinity. Okay, so the domain is all of our positive numbers and 0. That's the thing. Those are the things that we can plug into the square root. The range is going to be the outputs. And again, this graph covers everything from 0 up to infinity in the y direction. Okay, so our domain and range are both 0 to infinity. Now, for other radical functions, for other square roots in particular, the domain can be found in a similar way. We're just going to make sure that what's under the radical has to be greater than or equal to 0. So if I had a new radical function, let's say the square root of 2x minus 5, and I want to find the domain, well, I know that this stuff under the radical cannot be negative, right? So 2x minus 5 cannot be negative. If it was, I would have a non-real number answer, right? There'd be no real number. If this thing was a negative, I'd have the square root of a negative number. Can't have that. So instead, we're going to take that 2x minus 5, we're going to make it greater than or equal to 0, because that gives us our positive values and 0. And then we solve for x. 2x is greater than or equal to 5, divide by 2, and so x must be greater than or equal to 5/2, which is 2.5 or 2.5. Okay, so our domain then, x is greater than or equal to 2.5, will start at 2.5 and go to infinity. Right, so that's our domain. It's everything greater than or equal to 2.5. Now our range on this one is going to be the same, 0 to infinity. So I could even do a real quick sketch of the graph of this. 1, 2, 3, 4. If I knew that it starts at 2.5, 1, 2.5, and goes off to infinity, it's going to be doing something like this. Okay, so that gives us our correct domain. All right. Now the last thing is with this, the cube roots. And so cube roots, if I consider a new function, we'll call this one f of x again. Let's say f of x is the cube root of x. Well, with a cube root, you can have both positive and negative inputs to a cube root. So you can have 0, 1, what are perfect cubes, 8, 27, and so forth. But you can also have negatives, negative 1, negative 8, negative 27. And so when you calculate the cube root of 0, you get 0, cube root of 1 is 1, cube root of 8 is 2, cube root of 27 is 3, cube root of negative 1 is negative 1, cube root of negative 8 is negative 2, and cube root of negative 27 is negative 3. And so you have all these ordered pairs, but you have both positive and negative values. All right, so when we draw the graph, and I won't go through all the details of the graph, plotting the specific points, but what's going to happen is on the right-hand side, the positive values are going to have a similar curved shape to the square root. It's actually going to be a little bit stretched out, but similar. And on the negative side, you're going to have a mirror image down here underneath. Okay? And so this one, the cube root graph, has a domain that goes all the way to the left to negative infinity, all the way to the right to positive infinity, so it's all real numbers. And so also for the range. The range, this arrow goes down infinitely far, and this arrow goes up infinitely far. And so you have all real numbers for the range. There's no work to be done. A cube root will always have all real number domains and ranges.